Thank you. Hi, everyone. Thanks for the organizers to allow me to speak in front of you. And this is a part of my PhD work supervised by UQAM. So the plan for this talk is first talk about the motivation about this topic, and then go through some background about gentle algebras, representations of a gentle quiver, etc., and string combinatorics. And then we will go through the heart of the topic, that is the Jordan recoverability of a category. And then I will talk about some principal results and open questions that comes from these results. So the main motivation about this topic is to find an application of the Robinson-Chastain-Nuss correspondence in quiver representation theory. And in this point of view, Alexander Garver, Rebecca Patrias, and Hugh Thomas was able to show the following results. So here there is some terms that you don't know maybe, but I will define it during the talk. And just you can see that it is about quiver of ADE Dinkin type. And to prove this result, they use a variant or some sort of generalization of the RSK correspondence to give a bijection between a representation of the category and a tuple of integer partitions that will be called generic Jordan form that are of the representation. And one question I ask about it is if we can extend the result for gentle algebras. So now I will go through some recall about gentle algebras. So first, what is a quiver? You can just keep in mind that a quiver is like an oriented graph. You have here a finite set of vertices, finite set of arrows, and we will assume that the quivers are connected. So we will work also with path algebra. So here we will need an algebraically closed field, and to define the path algebra, you need to go through all the passes you have in the quiver, and you generate k-vector spaces with all the passes you have, and you have to undo this with a multiplication that will correspond to the concatenation of passes if it's possible, and if not, it will be 0. Then gentle algebras. To have a gentle algebras, you have some condition about the quiver. I will explain it in the next slide. And you have also to choose some path of length 2 to give you an ideal, and then you construct the quotient algebra from the path algebra with this ideal. So a proper definition about gentle algebra is the following. So you have a quiver with for any vertex, you have at most 2 rows ingoing and 2 rows outgoing. And your ideal must be an admissible ideal and must be generated by passes of length 2, such that for any rows alpha, you have some condition to satisfy, and you can just sum up things with the last figure of the slide, and we will call, just to make it short, a gentle quiver, a pair of a quiver and an ideal, such that the quotient algebra is a gentle algebra. Next, I will talk about representations of gentle quiver. So what is a representation of gentle quiver? You have a quiver, here an example, and you just place a k-vector space at each vertex, and you choose also a linear transformation at each arrows, and you have to satisfy the fact that if the concatenation of 2 arrows is in the idea, then the composition of the functions have to vanish. So yes, just a little thing about that. We can introduce the dimension vector of a representation that is just the vector of all the dimension of the vector space in your representation. So now about morphisms between representation, you have 2 representation, and a morphism between representation is a collection of morphisms between vector spaces at each vertex, and you have to satisfy the commutative square relations for like you can see at the end of the slide. And you can just have in mind this picture, just to have to satisfy for each rows alpha. We can call, we can talk about isomorphism between representations. We can also say that two representations are isomorphic to each other, and we can also talk about nilpotent endomorphism, like you can maybe think about it. And just for some of you that doesn't know very much things about representation, just a little thing to have in mind, that a representation is the same thing as a module following the last result. Here it is an equivalence of category between the two, so representation of the quiver and modules over the gentle algebra. So we can also define a direct sum between representations. So you can just have in mind the picture you have in the middle of the slide. So direct sum of representation will work like you think, I think. And then we can define, we can say that a representation that is a non-zero representation is indecomposable if you can't write it as a direct sum of representation. Then I will talk about string combinatorics. So string combinatorics is a tool that allow us to describe all the indecomposable representation that we have for a gentle algebra. So a string first is some sort of work in the quiver. You can follow arrows in the reversed orientation. So here is an example of a string. And you have also to avoid some little things. So you have to avoid composition of arrows that are in the ideal. And you have also to avoid the fact that if you follow an arrow, you can't follow the same arrow in the reverse orientation. That is the same thing that to say that the string is reduced. So some vocabulary around strings. We can talk about the length of the string, that is the number of arrows. We can talk about vertices support, row support. We can talk about substrings of the string. So it's just like subwords of the words which constitute your string. And we can talk about maximal string. So here you can see that we can't add another arrow at the vertex 1 or at the vertex 5, such that you get a more longer string. Then, more visually, we can represent strings like that with arrows pointing downwards. And we just recorded all the vertices we go through and all the arrows we go through. And if there is no ambiguity about the arrows we follow, we are following, we can just erase the arrows, but okay. Now, the link between strings and representation will go as follows. So we will follow this example. So with this example, take this following string, and with that string, we replace each vertex by a variable, a formal variable, and each arrows will say to you how the morphisms will go. So you take vector spaces generated by the formal variables that are in the same vertex. And you describe the morphisms thanks to like, for example, the arrow A just associate x1 to x2, x2 is associated to x3 by D, and so on. And you create a morphism like that, and you can take the isomorphism class of representation of this kind. So here is the proper definition, but I will not go through it. Just keep in mind the example. I think it's enough for this talk. And also, we can consider bands of the quiver, but there are some special kind of strings. And we can construct band representations that will not be isomorphic to string representation. But for this talk, you can just keep in mind that it exists, but I will not use it here. Just band representation is used just here. I will use it just for this result. So this result just classify all the indecomposable representation you have for a gentle quiver. And you can see that from the second point that if two string representation are isomorphic, that implies that the string is the same, or you have a reverse of the string. So we can identify a string to its inverse. That could be useful. And also just a little remark that morphism between string representation can be translated combinatorially in terms of special kind of substring, but I will not go through the details. So now about the heart of the topic, so Jordan recoverability of a category. So I will go with an example just to try to explain to you how it goes. So first, I need to define a generic Jordan form that of representation. So here we will take again this quiver. We will take again this representation, and I recall the decomposition of this representation, and I will try to describe all the nilpotent automorphism I can have for this representation X. So here some calculus, so we can see easily that n1 and n3 have to be 0, and then we have some work to do with bases. So we will take bases adapted to the decomposition, and then we will do some calculus just to know how it goes for the nilpotent automorphism at the vertex 2. That is the more difficult part, I think, in this calculus. At the end of all the calculus, we get the following form of the nilpotent automorphism of at the vertex 2. And among all the choices we can do to define the nilpotent automorphism at the vertex 2, so in fact, the nilpotent automorphism of the representation, there exists a generic one. So when I say a generic one, it's the same thing that to say that there exists an open-dense set in the set of all the nilpotent automorphism you can have in X. This open-dense set can be here characterized by the fact that you can choose alpha and delta non-zero. And this gives us the generic Jordan form data of X by taking the Jordan form data of a nilpotent automorphism in such a open-dense set. So just we can define things more properly. So first I have to talk about Jordan form data of an nilpotent automorphism. So a Jordan form data of an nilpotent automorphism is just a recording of the Jordan forms of each nilpotent automorphism at each vertex Q, and you take the partition as all the size of the Jordan blocks you have in each Jordan form of your nilpotent automorphisms. And just little thing, nilpotent automorphism set will be written like that. And there is a result from Garver, Patrias, and Thomas, the same paper, that says that the set of nilpotent automorphism of X is an irreducible algebraic variety. And moreover, there exists a maximal value of Jordan form data in the sense of an extension of a dominance order. I will not recall it here, but just dominance order, just an extension. You can define a dominance order on partitions and just try, extend this. This maximal value is attained by an open dense set of nilpotent automorphisms. And this maximal value is exactly what we will define as the generic Jordan form data of X. So now just a question that can arise from all of this is, from which subcategory C of a category of all the representation of the quiver could we recover up to isomorphism a representation of the category C from a generic Jordan form data, its generic Jordan form data? And the answer of this question is a definition, here the definition of Jordan recoverability of a subcategory of representation. So here is just the fact to say that for if you have a generic Jordan form data from a representation of your category, then you can recover the representation from its generic Jordan form. I hope I was clear. So here are some example. The first category, you see that it is the additively generated by the indecomposable we already saw previously. And this category is Jordan recoverable, and it is not so difficult to see that why it is Jordan recoverable. But the category of all the representation of the quiver in general, it is not Jordan recoverable. And here just an example with simples. So when I wrote ME1, it's the simple at 1, simple at 2, 3 times, and then simple at 3 1 time. You will get the same Jordan generic Jordan form data than X. So this is not Jordan recoverable. And you have to know that in general, it is not easy to know whether or not a category is Jordan recoverable. So we will do a refinement of the property to be Jordan recoverable. And the question you have to ask is there a way to recover a representation from a generic Jordan form data? Because I don't explain here, for the moment, I don't explain how to recover a representation from a generic Jordan form data. So I will go through the same example. So we take again the same representation. We know now the generic Jordan form data of this representation. And now I will take a representation Y of in all the representation we have in the quiver. And I will ask for this representation to have the same generic Jordan form data than X. And I will take then an important automorphism of Y that have Jordan form data that is the same of the generic Jordan form data of Y. And I will try to describe all the representation Y that satisfies the conditions that I give you here for Y. So here are some calculus. And at the end of all the calculus we can get, we can get again an open dense set in which we will have all the representations that will be isomorphic to X. Here you have to choose alpha prime non-zero and beta prime non-zero. So thanks to this condition, we recover X from its generic Jordan form data. So there is some. So this technique can be generalized, but it uses something more stronger than Jordan recoverability, and this is what we call the canonical Jordan recoverability of a category. So this time I ask for each representation in the category that there exists a dense open set O in all the set of representation of the quiver that has the same generic Jordan form than X, such that all the representation in the open dense set are isomorphic to X. So here are just 2 examples. So again, the same example as before is canonically Jordan recoverable, and there is something similar proof that works from the previous calculus, but I don't give the details. So okay, and if you take the category of all the simples, this time this is Jordan recoverable, but not canonically Jordan recoverable, and that's something you can keep in mind. So you can see that canonically Jordan recoverable category is a Jordan recoverable, sorry. And there is some example in which you can see that there is, for a tuple of integer partitions, you can see that we can not always have an open dense set in which all the representation will be isomorphic to each other. So here is a Kronecker quiver, and we have also an example. I can show you an example for the quiver we work with. So okay, I will just introduce some definitions, and the result and just end because I saw that I will just out of time. So the next definition is just what about the category CQM. So the category CQM is the subcategory additively generated by all the indecomposable representation X of the quiver, which are supported at the vertex M. So the category we saw earlier is one of the kind. And the definition of minusculity here. So a vertex will be said to be minuscule even only if any indecomposable representation, is such that the dimension of the vector space at the vertex M is less than or equal to 1. So I had a little game, but unfortunately I have not the time to do that. But the little game is just to play with your feelings about what you understand about all the things I talk about. And you can see here in this result that to be minuscule, it will be not enough to have a Jordan recoverability or canonically Jordan recoverability of a canonical Jordan recoverability of a category. And I have a result here that is described, that is a characterization of any category CQM that are of the kind, and it is really based on string combinatorics. So all the things are said in string combinatorics, and all the proof goes with string combinatorics. Okay, so I will just show some open question we can ask. Oops, sorry. Some questions we can ask about the result, following the results, and so that's all. So thank you for your attention.